Hello, this is Professor Roman. Welcome back to the lecture series Transition to Advanced Mathematics. Well, we have finished our discussion of logic, both the propositional and the predicate calculus. So it's time to move on to the second main goal of this course, which is proof techniques. There are no algorithms for constructing proofs. Every proof is unique and generally will incorporate some key ideas that make the proof work. And these key ideas may be relatively simple or they may be extremely difficult to spot. For example, in the last 275 years, no one has been able to figure out the key ideas necessary to prove or disprove the Goldbach conjecture. Some results have relatively simple proofs that can span a line or two or a paragraph or two. Some proofs are a bit more involved and can take a page or two, but some proofs can be quite complex and require many pages. As an extreme example, there's a very famous theorem belonging to the field of group theory called the Fate-Thompson theorem. And this proof required 255 pages to complete. Also, it often happens that the first proof of a result is not as elegant or streamlined as it might be. Just as an example, suppose you were to find a proof of the Goldbach conjecture. You would probably be much more interested in when you were going to get your $1 million and all the job offers that will be pouring in from major universities, rather than trying to reduce your proof from, let's say, 50 pages to 40 pages. I'm not saying it's something you wouldn't do, but it wouldn't probably be your first priority. First proofs are often the result of very original and brilliant thinking, and so one turns his attention to something else rather than reworking the proof to improve the pedagogy. As an interesting example, there's a theorem in group theory called Cauchy's theorem, and it's one of the fundamental results in all of group theory. Its proof has a very colorful history. The theorem was first proved by Augustin Louis Cauchy in 1845 as the main conclusion of a 101-page paper. Cauchy was one of the most brilliant algebraists of his time, mathematicians, in fact, of his time. An article was written by a man named M. Mayo entitled The Mathematical Life of Cauchy's Group Theorem. And I have a citation here if you want to look at the full article, some 25 pages. But here's a quote from the article. The initial proof by Cauchy, however, was unprecedented in its complex computations involving permutational group theory and contained an egregious error. A direct inspiration to Silo's theorem, which is another one of the fundamental theorems in group theory, Cauchy's theorem was reworked by R. Dedekind, our friend Richard Dedekind we've talked about, Frobenius, Jordan, and McKay in ever more natural, concise terms. Well, today we have proofs that span less than a page. So Cauchy, who was a brilliant mathematician, didn't quite see the key ideas required to produce a short and accurate proof, of course. It's also interesting to note that even a mathematician of Cauchy's quality could publish a paper with a bad error. It's not something we like to do. And it shouldn't be an excuse for any of the rest of us to do so. The only way to become skilled at proof making is to practice. You shouldn't be discouraged if it seems to be slow going. Proof making is a skill in itself, and it can take years to develop that skill. It's not something you can learn in a single course like this one. What I can help you with is understanding the general techniques or approaches to constructing proofs, and that's what we will do. Beyond that, it's going to be up to you to practice, practice, practice. The more you practice, the better you will get at proof making. It only stands to reason. That's the way it is with everything in life. There are two separate aspects to good proof construction. One aspect, of course, is finding the actual mathematics that forms the content of the proof, especially those key ideas we talked about. Without this, of course, you have no proof, and so this must be the most important aspect of proof making. But there's another aspect that doesn't get the attention that it deserves, and that is good writing style, good communication skills when you write your proofs. This is a separate skill. There are many brilliant mathematicians who do not communicate mathematics well. It happens. It's a different skill. It's a separate skill. But for obvious reasons, good writing style and good communication skills don't get the same level of attention as good original mathematics does. But nonetheless, it is important. And for you, it is particularly important because what you write, when you write proofs, someone else is going to be judging them and grading you, giving you a grade as a student. And so the better your writing style, the better you communicate your thoughts, the more easily the grader will be able to understand what you're doing. Remember, the person who's sitting in judgment on you on these things is taking an objective position. I don't know anything. Is this proof going to teach me what I need to know? And does the author of the proof, does the author of the proof understand what he or she is writing and doing? So these are important things. In fact, even after you graduate and take a job, whether it's teaching mathematics or not, you're still going to be judged on your communication skills. One of the goals of good proof writing, of course, is to make what you are writing, to make the proof clear, relatively easy to understand by others. But there is a little bit of an irony here that's very seldom mentioned out loud, and that is there's such a thing as being too clear when writing proofs that are intended to teach others. So this applies to this textbook and other textbooks. It's vitally important for students to begin to think for themselves. And if a teacher fills in, or author fills in all of the blanks in a proof, anticipates every question, and fills in the answers, leaving no gaps, that isn't really doing the student a service. Students may think it is, but it's not, because students need to be challenged to some degree so that they can get sufficient practice in thinking for themselves. Okay. So, enough commercial. Let's get down to business. Speaking very generally, a proof of a theorem consists of a finite sequence of statements, whose final statement, T, is the conclusion of the proof. The statements S1 through Sn that lead up to the conclusion, to the final sentence in the proof of the theorem, those statements generally take one of two forms. They will mention a previously proven result, a theorem, a lemma, a corollary. I'll just call them results. Or they may be statements that are logically equivalent to earlier statements in the proof. Generally speaking, theorems in mathematics take the form of a conditional statement, if P then Q, where the antecedent P consists of 0 or more hypotheses or assumptions or premises, all the same thing. There doesn't need to be any, but there may be hypotheses. And the conclusion, Q, the consequent is the conclusion of the proof. So here's an example of a theorem with a single hypothesis and a single conclusion. If n is an odd integer, that's the hypothesis, then n has the form 4q plus r, where r is 1 or r is 3. That's the conclusion. And I'm going to prove this for you in a few minutes. Here's an example of a theorem with no hypotheses, but just a single conclusion. There are infinitely many prime numbers. So as I mentioned, it's quite common in proofs to see references to previously proven results. Phrases such as, according to theorem x point y, we have the following, or theorem x point y implies that, and we have the following. It's important to understand mathematics builds upon itself. You can't isolate one subject or one idea separate from all other ideas in mathematics. This is why it is so important to absorb, to understand previous results, because they may provide the key ideas for the proof you're currently trying to construct. To draw an analogy, you can think of every theorem, corollary, lemma, proposition, every result that you encounter as a tool for use in later proof making. Each time a result is proved, it should go in your toolbox. Then, when you need to construct a new proof, or if you get stuck in the middle of constructing a proof, you can look through your toolbox. You can review earlier results looking for tools that may seem relevant to the proof you're working on. It may jar your brain in coming up with an idea. Gee, maybe this earlier theorem is applicable here. That sort of thing. In fact, let me give you two tools right now to place in your toolbox. The first one is the division tool, and it's officially called the division algorithm. If a and b are integers with a not 0, then there are integers q and r for which b equals qa plus r, where r lies between 0 and a minus 1, it's strictly less than a. The integer q is called the quotient, and the integer r is called the remainder. Well, this is stuff I'm sure you know, but here it is laid out formally as a theorem and given a name, division algorithm. So you now have this tool in your toolbox. As you construct proofs, it may occur to you that I need to divide something into something else. You have the division algorithm. We're going to use it as well, many times in fact. Here's another tool that should be in your toolbox. It's Bezos' lemma. We talked about that earlier in the lecture series. Here is a formal statement, more elaborate than the lemma that I gave you way back when. Let a1 through an be integers with greatest common divisor d. Then there exist integers alpha 1 through alpha n for which d is equal to this expression. This is officially a linear combination of a1 through an with coefficients alpha 1 through alpha n. If you've taken linear algebra, you'd recognize that term, linear combination, but we can just call it a combination for now. This is called Bezos' identity. Perhaps the most useful case of Bezos' lemma is for integers that are relatively prime. In fact, integers a1 through an are relatively prime if and only if there exist integers alpha 1 through alpha n for which this combination, this linear combination, is equal to 1. This is a very handy fact. In fact, every time you encounter relatively prime integers, whether it's 2 integers or 10 integers, your mind should immediately go to Bezos' lemma, because there's a strong chance that Bezos' lemma is going to help in whatever you're doing. It's not 100%, but it's a very handy tool to have in your toolbox. There will be probably many times when you're constructing a proof that you'll come to a point where you don't know what to do next. You get stuck. It happens all the time. It happens to me all the time. When that happens, here is my advice. First, reread the theorem to be sure that all of the hypotheses as well as the conclusion are fresh in your mind. That alone might jar your mind to produce a new idea and take another step in your proof. Reread the part of the proof that you've constructed thus far to the point where you got stuck, looking especially for mistakes. We all make them. I make plenty. If you've made a mistake, it shouldn't be surprising that you're stuck. Okay? Even if sometimes you'll make a mistake and finish a proof and think you have a valid proof. I guess Cauchy did that. And yet the proof is worthless, potentially worthless if there's a mistake. And there may be some good ideas in the proof you can salvage, but the proof itself as a whole is worthless. So it's vital to check for mistakes. But also, as you read each line in your argument, assuming they're valid, of course, ask yourself the question, is there some other logically equivalent way I can say what I just said? It's surprising how often rewording a statement in different ways, logically equivalent ways, will trigger a new idea. Another piece of advice is work from both directions when constructing a proof. There are many proofs that are more easily constructed by working from both ends working forward from the hypotheses, working backward from the conclusion. I'll give you an example in a minute, but the general idea is, suppose you have started with the hypotheses and you've made some progress. So you've written a partial proof and then you get stuck. If this happens, and it will, turn to the conclusion. Turn your attention to the conclusion and see if you can work backwards by asking yourself questions such as, how else can I write the conclusion? Or what possibly relevant statements can I think of that imply the conclusion? You might be able to build a chain marching backwards here from the conclusion, and then all you need to do is connect these two chains. In other words, you need to figure out how to go from SK to T1. So before you worked backwards, you were trying to go from SK to C, and that might be too big a jump. But if you can take some steps backwards, the jump from SK to T1 might be smaller. It might be easier to spot, figure out how to take that jump. That's the general idea. Let's look at proofs of the two theorems that, the proof of the first theorem that we looked at and proof of another theorem. Here's this theorem. I've reproduced it here. If n is an odd integer, then n has the form n equals 4q plus r, where r is 1 or r is 3. This theorem, as you look at it, begs for the division algorithm, which tells us that n can be written as 4q plus r, where q is the quotient and r is the remainder, so r lies between 0 and 3, because we're dividing by 4. Now our goal is to show that r has to be either 1 or 3. But if r is 0, then n equals 4q, and that's even, contrary to the assumption that n is odd. So r cannot be 0. Similarly, if r is 2, then you get n equals 4q plus 2, which is also even, another contradiction to the oddness of n, so r cannot be 2. And that leaves only the possibilities r equals 1 or r equals 3, and proves the theorem. Notice in this proof that I wrote complete, grammatically correct sentences. There are no partial sentences. They're all complete sentences with punctuation and everything. Okay. Notice also that I clearly explained what the symbols mean. Q is the quotient, R is the remainder. Notice also that I explained here, our goal is to show that r equals 1 or r equals 3, that this sentence tells the reader what we are planning to do, what we must still do. Okay. This is such a short proof that I probably could have left out that sentence without any real damage, but the process here of learning proof techniques, we're applying it to relatively short proofs, but it's going to be, you're going to need it for longer proofs even more. So it's important to do things like this here. Okay. So I have tried to guide the reader step by step through a valid argument that leads to the conclusion of the theorem. Pay a special attention to writing complete sentences. I, as a professor of over 40 years, have seen hundreds, thousands of proofs written by students. And for the most part, students do not use complete sentences. You're not just writing mathematics, you're writing prose, you're writing a novel, a one-paragraph novel. You're trying to communicate. So you need to pay attention to full sentences, to explaining all the symbols. I can't tell you how many times in a student's proof an X just appears out of nowhere. I don't know whether it's a real number or an integer or a positive real number. I have no clue. Remember that you are going to be judged on your proofwriting skills. A professor or grader is going to look at what you wrote and say, and pretend they don't know how to do the proof and say, is this a convincing argument? Does the author of the proof understand the proof? And has he or she communicated it to me accurately and clearly? That's all part of the game. It's not just the mathematics. It's the communication of that mathematics that is important. Here's an example of a proof working from both directions. It's very short, so it's not a complicated example. I'm going to include some, at least a couple cases, some parenthetical remarks in the proof, and I'll put them in square brackets. This is thinking out loud. This would not be normally not be included in a proof, but since you're in the business of learning proof techniques right now, I wanted you to see my thinking. Okay. Let a, b, and c be real numbers. If a plus b is not 0, and a squared equals ac minus ab plus bc, then the straight lines L1, y equals ax plus b, and L2, y equals cx plus d, in the plane are parallel. Well, as I look at this, first I read the hypotheses, and I am not sure how to use these algebraic equations to produce a geometric result, parallelism. So I look at the conclusion. How else can I write the conclusion? Answer, as you no doubt know, and this is where the proof can start, two lines are parallel if and only if they have the same slope. That should be the first sentence in your proof. Something about the conclusion rather than something about the hypotheses. The slope of L1 is A, and the slope of L2 is C, and so the proof will be complete if we can show that A equals C. Okay. Again, as a thinking out loud, we now have a new conclusion, and it's no longer geometric, it's algebraic. We can forget about the lines right now. All we have to do is connect this algebra to this algebra, A equals C. So we reduced the problem to one of pure algebra. And the proof continues. Using the second hypothesis in 4.7, notice I've numbered the hypotheses so I can refer to them. We have second hypothesis, move everything to one side of the equal sign, factor. But the first hypothesis tells us that a plus b is not 0, and so we know that a minus c must be 0 if the product is 0. In other words, a equals c, and the proof is complete. When you take out this parenthetical remark and this one, you have a pretty brief, pretty short proof, but complete sentences, the first step was working backwards from the conclusion, then connecting the hypotheses with that. we will discuss several templates that can be used to help construct proofs. You can think of these templates, this is my word, template, I don't think you'll see it elsewhere, but you can think of templates as general guides in developing a proof. A proof template won't tell you what to say, but it will tell you how you might approach the overall construction of the proof. In fact, it's often going to be unclear which template is the best one to try. Only experience will allow you to improve your guesses. We all guess, I guess, everybody guesses as to how to approach a proof. But the more experience you have, the better your guesses are going to be. Also, many times more than one template will work, so that's nice. But the problem of deciding which template to try first, that's not something I can teach you because it varies with each proof. Some things we can address at a very general level before we get to the templates is that it's common to see statements of theorems that have one of a certain number of forms. They're all the conditional statements. And when you do see one of these forms, or 6 of them will go through, that will provide a guide as to, this material will provide a guide as to how to approach that. So if the theorem has symbolic form P and Q implies R, then we are allowed to assume both P and Q, and we try to prove R. Okay. If, on the other hand, the statement of the theorem has this form, P implies Q and R, then we must really prove 2 things, that P implies Q and that P implies R. So this may require 2 separate and conceivably totally different proofs combined into one bigger proof. So a proof like this should, if that's what you're going to do, the first sentence in your proof should be that we will, something like, we will prove P implies Q, and then we will prove P implies R. Okay? So you tell the reader what's coming. If the statement of the theorem has this symbolic form, P or Q implies R, you again have to do 2 things. You have to show that P implies R and that Q implies R. If the statement of the theorem has this symbolic form, P implies Q or R, this one's a little bit trickier. You might be able to do this directly, assume P and show that Q or R must hold, but oftentimes the best way to approach this is to assume P holds and not Q, that Q does not hold, and then prove that R holds. If you can do that, then you can reason as follows. Well, we assume that P holds, which we're allowed to do. If Q does hold, we're done. Then P implies Q or R. If Q fails to hold, then the proof of this will still show that R holds. This is the same as this, but the roles of Q and R are reversed. There's a symmetry here between Q and R. Sometimes proving one of these 2 will be simpler than proving the other. So, and which one, who knows? You have to, it just depends on the situation. But the idea is to assume P and assume that one of these fails and show that the other one then must hold. If you have a theorem of the form P implies Q implies R, then you are allowed to assume P in order to prove that Q implies R. But to prove Q implies R, you are allowed to assume Q. So in effect, you are allowed to assume both P and Q in order to show that R holds. That is the same as this. Assume P and Q, show that R holds. And indeed, if you start with this by a series of logical equivalences, you can reach this. And I'm not going to go through this now because I think it would be good practice for you to do it. Finally, if your theorem has the form P implies Q implies R, you are allowed to assume that P implies Q, and you must prove that R holds. But you are not allowed to assume P holds. Only that P implies Q holds. And if you remember the truth table for the conditional, P implies Q will hold if P is false. So if you assume P is true, you are not going to get a full proof because you must take cases where P is false as well. Okay? So this is something to think about here until it's clear. Now, P implies Q is logically equivalent to not P or Q. We talked about that some time ago. So this conditional is logically equivalent to this one. And now you can approach the proof of this by proving that not P implies R and also that Q implies R. So you can break this down into two proofs. Before we start looking at the templates, the proof templates in detail with examples, I want to go over them with you. Without the examples, just go over the templates so you can get the full picture of what's going on. The first template is a direct proof template. A direct proof applies to theorems that are generally of a conditional form, and it's a very simple template, although execution may not be simple. Assume P and deduce Q. I guess you can see from this there's not a whole lot I can tell you about direct proofs in general. Everyone is different. All I can tell you is assume P and try to deduce Q. A proof by contraposition also applies to conditional statements. It's nothing more than a direct proof of the contrapositive. As you know, the contrapositive is logically equivalent to the original, so a proof of either one gives you a proof of the other automatically. So we assume not Q, we deduce not P, and then say something like, well, we have proven that not Q implies not P, therefore P implies Q. For proofs by contraposition, the first sentence in your proof should be, our proof is by contraposition, or some words to that effect. Even just the 3 words, proof by contraposition, period. It's important to tell the reader which template you're using for these 2 templates. Direct proof, you don't need to say, we will prove the result using the direct proof. That is pretty obvious when it happens. But it's very important to tip off the reader or the grader that you're using proof by contraposition. You can even do that by starting with the first sentence by saying, we will prove the contrapositive of the theorem. Anything that tells the reader what you're doing. Proof by contradiction. This applies to any proposition, P. It doesn't have to be a conditional. And it works as follows. You assume that the proposition is false, and you deduce a statement that is obviously false, that is contradictory. For example, 0 equals 1. That's a great one if you can manage it. Or x equals 1 and x does not equal 1. These are obviously false. They are contradictions. And so if your assumption of not P leads to a false statement or a contradiction, then you know your assumption must be wrong. Well, if not P is false, P is true. That is proof by contradiction, and again, you should state that at the outset. Proof by contradiction, or we will prove the result by contradiction. Okay. You could even start by saying, assume the statement of the theorem is false. Assume not P. That will tip off everybody that you're proving by contradiction, so that's fine. Biconditional statements can be proven sometimes in two different ways. There are two different templates for that. I call this a two-part proof. That's just a name. You might not hear it anywhere else. But what that is the biconditional is logically equivalent to the conjunction of P implies Q and Q implies P, statement and its contrapositive. So to prove this biconditional, you can prove P implies Q and Q implies P, and that will tell you that will give you the proof. Okay? And that is generally the most common way to prove biconditional. And again, here you should start your proof by saying, first, we will prove P implies Q. And you have to write that out. You're not going to literally say P implies Q. You're going to write out what that means based on the theorem at hand. And once that proof is completed, you would then write a sentence such as, now we will prove Q implies P. Or now we will prove the contrapositive. I'm sorry, that's it. Now we will prove the converse, Q implies P. Okay. So you have clearly defined what you're doing. And then at the end you say that we've proven both this statement that P implies Q and Q implies P, therefore P holds if and only if Q holds. Another way to approach the proof of a biconditional, which I think is less common but does work, is sometimes you can produce a chain of biconditionals, starting with P if and only if R1, R1 if and only if R2, and so on until you get to Rm if and only if Q. This shows that P holds if and only if Q holds. This is less common, but when it works quite well. Okay. So I call this the chain type proof because this is a chain of biconditionals linked together. Right? The R1 is the same here as R1, R2 here matches R2, and so on. Okay, so we are ready then to take a close look at the templates with examples. As you look at the upcoming example proofs, you should pay attention not only to the mathematical content and how it's organized, but also to the style in which the proof is written. I'm not suggesting that my proof writing skills are any better than anyone else's, but I have had 40 years or 50 years of practice. So at least they will give you some ideas on how you want to write your own proofs. There's no such thing as the right way to do a proof. If you sat 10 mathematicians down and asked them to prove something, you would get undoubtedly 10 different proofs. Now the mathematics might be consistent, but even that there's different mathematics that can lead to the same conclusion. But you will probably get 10 different writing styles. So the proofs will look quite different. There's nothing wrong with that. Writing, communicating mathematics can be done in many ways. So you should develop your own style. But hopefully the proofs you read in this book will help you to decide how to develop your own style.